Hello, and welcome to this lesson on integration examples. This particular lesson takes several of the integration techniques and it applies them in some formats that you might not have seen in previous examples. So let's take a look at example 1. So example 1 says find the indefinite integral of the following. So we have the indefinite integral of 9 over x squared plus 16 dx. So for the solution to this, we're going to bring out the coefficient, the 9, and that gives us 9 times the integral of 1 over the square root of x squared plus 16 dx. Now this fits our formula for arctangent. So still have my coefficient in front, and that's going to be 1 over 4, that's the square root of 16, times the arctangent of x over 4, and then plus a constant. And then the 9 times the 1/4, that gives us a 9/4 times the arctangent of x over 4 plus a constant. And that's our answer, 9/4 times the arctangent of x over 4 plus a constant. All right, the next example is similar to the first one. The only difference is instead of having just a coefficient in the numerator, we've got a 9 times an x, a variable. So for this one, again, we're going to take that coefficient out, so this gives us 9 times the integral of x over x squared plus 16 dx. So for this problem, we're going to use u substitution. So if there was just a single number on top, that used our arctangent formula. But now that I've got an x on the top, I'm using u substitution. So u is equal to x squared plus 16 du, the derivative of u, that's going to equal the derivative of x squared plus 16, which gives me a 2x times dx. Solving this equation for dx, that gives me dx is equal to du over 2 times x. We are now going to substitute these u's into my integral. So this gives me 9 times the integral of x over u times du over 2 times x. The x's will reduce, and then this is going to give us a 9 over 2 times the integral of 1 over u du. Integrating this, well, the integral of 1 over u, that's going to be the natural log. So we have 9/2 times the natural log of the absolute value of u plus a constant. And then u, that was x squared plus 16. So I have 9/2 times the natural log of x squared plus 16 inside of absolute values plus c. Now, since x squared plus 16 is always going to be positive, this can be rewritten as 9/2 times the natural log of x squared plus 16 in parentheses plus a constant. And that's my answer, 9/2 times the natural log of x squared plus 16 plus a constant. Let's take a look at the next example. So the next example is kind of like the previous one. The only difference here is instead of having a plain old x, I have an x squared. Now for this one, since the exponent on top happens to be equal to the exponent on bottom, I'm going to do a long division problem first. So again, this is something that we have seen a long time ago with integrals, and that was if the exponent on top is equal to or greater than the exponent on bottom, then we have to divide this. So again, bringing my coefficient out in front, so it's going to be 9 times, and then setting up my long division, x squared plus 16 on the outside. On the inside, I've got x squared plus no x's and plus no constant term. Well, x squared divided by x squared is 1. 1 times x squared is x squared. 1 times 16 is 16. And then when I subtract this, x squared minus x squared, that goes away. And then 0 minus 16 gives me a negative 16. So this fraction, x squared plus 16x, that can be rewritten as a 1, my quotient, minus, because it was a negative 16, 16 over x squared plus 16, my divisor. Now this is something that we can integrate. Still have this coefficient out in front. The antiderivative of 1, that's going to give me an x, so that should be an x there, not a 1. That should be an x. And then I'm going to have 16 times 1 over 4 times the arctangent of x over 4, and then plus a constant. Now the 16 and the 1/4, that's going to reduce to a 4, and then when I distribute the 9 through, that gives me a 36. So this should be 9 times x, this should be a 9x here, minus 36 times arctangent of x over 4 plus a constant, which then gives me my answer of 9x, that should be an x there, minus 36 times the arctangent of x over 4 plus a constant. Let's take a look at the next example. So find the indefinite integral. So I have x plus 9 over the square root of 16 minus x squared. Now since I have two terms on the top, what I'm going to do here is break this up into two fractions. So first one's going to be x over the square root of 16 minus x squared, and the second one is 9 over the square root of 16 minus x squared. So this can be rewritten as two separate integrals. One of them is the integral of x over the square root of 16 minus x squared dx plus 9 times the integral of 1 over the square root of 16 minus x squared dx. For this first integral, I'm going to use u substitution. So u is going to equal to the stuff inside my square root. U is equal to 16 minus x squared. So then du is equal to negative 2x dx. Solving this gives me dx is equal to du over a negative 2x. So for this first integral, substituting in my u's and my du's, this is going to give me x over the square root of u. This 16 minus x squared is going to become a u. And that's going to be times a du over a negative 2x. Well, the x's are going to reduce, and that's going to give me a negative 1/2 times the integral of 1 over the square root of u du. And the second integral over here, I haven't done anything with that. Rewriting this 1 over square root of u, that ends up giving me a negative 1/2 times the integral of u to the negative 1/2 times du. So integrating these, this first one's going to integrate. That's going to give me a negative 1/2 times, I have to add 1 to the exponent. So negative 1/2 plus 1 gives me a positive 1/2. And if I divide by the new exponent, dividing by 1/2, that's going to give me a positive 2. So I get negative 1/2 times 2 times u to the 1/2. Plus, integrating the second one, I'm going to have a 9 in front. And this over here is going to be my arc sine. So I get the arc sine of x over 4 plus a constant. All right, replacing my u with the 16 minus x squared, and the 1/2 and the 2 reduces. So I've got a negative 16 minus x squared to the 1/2 exponent plus 9 times the arc sine of x over 4 plus a constant. So that gives me my answer, negative 16 over x squared raised to the 1/2 exponent plus 9 times the arc sine of x over 4 plus a constant. All right, so let's take a look at another one here. So we want to find the indefinite integral. So here I've got the indefinite integral of x over the square root of 16 minus x to the 4th. So my solution here, I've got u squared is equal to x to the fourth, which gives me u is equal to x squared. When I calculate du, this gives me du is equal to 2x times dx, which gives me dx is equal to du over 2x. So now, when I do my substitution, this gives me the integral of x over the square root of 16 minus u squared times du over 2x. Well, my over 2, that's going to become a 1/2 times the integral of 1 over the square root of 16 minus u squared times du. This is going to use my arcsine formula. So I'm going to have 1/2 times the arcsine of u over 4 plus a constant. And then u was equal to x squared. So I get 1/2 times the arcsine of x squared over 4 plus a constant. And that's my answer. 1/2 times the arcsine of x squared over 4 plus a constant. All right, let's take a look at this example. So finding the indefinite integral. So this one here doesn't quite match our templates that we have seen. So I'm going to rewrite this one. What I'm going to do here is on the numerator, I'm going to add e to the 2x, and I'm going to subtract e to the 2x. So I get 1 plus e to the 2x minus e to the 2x all over 1 plus e to the 2x. If I break this up into two fractions, I get 1 plus e to the 2x over 1 plus e to the 2x minus e to the 2x over 1 plus e to the 2x dx. The first fraction reduces to a 1. So this gives me 1 minus, or the integral of 1 minus e to the 2x over 1 plus e to the 2x dx. So I'm going to break this up into two integrals. So I've got the integral of 1 dx minus the integral of e to the 2x over 1 plus e to the 2x dx. Integrating the first one, that gives me an x minus, now we're going to have to deal with the second integral, the integral of e to the 2x over 1 plus e to the 2x dx. Using u substitution, u is equal to 1 plus e to the 2x. du is equal to 2 times e to the 2x dx, which gives me dx is equal to du over 2 times e to the 2x. So now if I substitute, well, I've got x minus the integral of e to the 2x over u times du over 2 times e to the 2x. The e to the 2x's cancel, and I get x minus 1/2 times the integral of 1 over u du. So if I integrate 1 over u, that's going to end up giving me a natural logarithm. So I've got x minus 1/2 times the natural log of the absolute value of u plus a constant. Well, u gets replaced with 1 plus e to the 2x. So I've got x minus 1/2 times the natural log of the absolute value of 1 plus e to the 2x plus a constant. Now, e to the 2x, that's always a positive number. Plus 1, it's always going to be a positive number. So this can be rewritten as x minus 1/2 times the natural log of 1 plus e to the 2x plus a constant. And that's my answer. X minus 1/2 times the natural log of 1 plus e to the 2x plus a constant. All right, let's take a look at another one here. So number 7, example 7, find the indefinite, or find the, there should be indefinite integral of tangent of x times, the natural log of the cosine of x dx. So using u substitution, I'm going to let u equal to the natural log of the cosine of x. When I take the derivative of u, the derivative of natural log, that gives me a 1 over, so I get 1 over cosine of x. And then times the derivative of the inside, the derivative of cosine is a negative sine of x dx. Well, that gives me a negative sine of x over cosine of x dx. Sine of x over cosine of x, that is tangent of x. So I have du is equal to the negative of the tangent of x dx. Solving this for dx, I get dx is equal to the negative of du over the tangent of x. So if I substitute, I now get the integral of tangent of x times u times a negative du over tangent of x. My tangents cancel, and I get the natural log, I get the negative of the integral of u times du. So when I integrate, I add 1 to the exponent, divide by the new exponent. So I get a negative 1/2 times the natural log of u squared plus a constant. And then u was that natural log of cosine of x. So this gives me negative 1/2 of the natural log squared of the cosine of x plus a constant. And that's my answer. Negative 1/2 times natural log squared of the cosine of x plus a constant. All right, let's take a look at another one. So we want to find the indefinite integral of tangent squared of x. So using a trigonometric identity, tangent squared of x is equal to 1 minus secant squared of x dx. When I integrate, the integral of 1 gives me an x. The integral of secant squared gives me a tangent. So I've got x minus the tangent of x plus a constant. And that's my answer. Number 9, find the indefinite integral of sine squared of x dx. So sine squared of x, using a trigonometric identity, sine squared of x, that becomes 1 minus cosine of 2x over 2. So bring my over 2 out, that gives me a 1/2 times the integral of 1 minus cosine of 2x dx. Integrating, well, the 1 becomes an x, minus the antiderivative of cosine gives me a sine, and then I've got to divide by that coefficient in front. So I've got 1/2 times x minus a 1/2 sine of 2x plus a constant. Distributing my 1/2 through, this gives me a 1/2 x minus 1/4 times the sine of 2x plus a constant. So that's my answer. 1/2 x minus 1/4 of the sine of 2x plus a constant. Now let's take a look at this next example. So we want to find the indefinite integral of x plus 1 over x squared plus 6x plus 9. All right, so my solution, using u substitution, this gives me, u is going to be x squared plus 6x plus 9. Du is going to be 2x plus 6 dx. Dx is going to be du over 2x plus 6. In order for u substitution to work, that numerator has to be a 2x plus 6. So we need to rewrite that numerator. The first thing we need is a coefficient of 2 in front of the x. So we're going to multiply the top of our fraction and the bottom of our fraction by 2. Distributing 2 through the top, that gives me a 2x, which is what I needed, plus 2. And in the 2 on the bottom, I'm going to write that as a 1/2 in front of my integral. So I have the integral of, I got 1/2 times the integral of 2x plus 2 over x squared plus 6x plus 9 dx. We now need a constant of 6 in the numerator. So I have a 2. In order to get a 6, I'm going to add 4, and then I'm going to subtract 4, and that will give me a 6. So I get 2x plus 2 plus 4, which gives me 2x plus 6, and then a minus 4. Breaking this up into two fractions, I've got 2x plus 6 over x squared plus 6x plus 9 minus 4 over x squared plus 6x plus 9 dx. Breaking this up into two integrals, I've got 1/2 times the integral of 2x plus 6 over x squared plus 6x plus 9 dx minus 1/2 times 4 over, or the integral of 4 over x squared plus 6x plus 9 dx. If I bring my 4 out, 4 and 1/2 reduces, that gives me a 2. And then this bottom factors into an x plus 3 times an x plus 3, which is x plus 3 squared. All right. So now, using my u substitution, substituting into the first integral, this ends up giving me 1/2 2x plus 6 over u times du over 2x plus 6 minus, and there's my second integral, not changed. The 2x plus 6 and the 2x plus 6 reduces, so I've got 1/2 times the integral of 1 over u du minus 2 times the integral of 1 over x plus 3 squared dx. The antiderivative of 1 over u, that gives me the natural log of the absolute value of u. So I have 1/2 times the natural log of the absolute value of u minus 2 times the integral of 1 over x plus 3 squared dx. Well, u is equal to x squared plus 6x plus 9, which is the same thing as x plus 3 squared. So I've got 1/2 times the natural log of the absolute value of x plus 3 squared minus 2 times 1 over x plus 3 squared dx. We're now going to do a substitution on the second integral. Since we have already used the variable u, we will use the variable v in the substitution method. So v is going to be x plus 3, which means dv is equal to dx. So if I substitute in that second integral, I've got 1/2 times the natural log of the absolute value of x plus 3 squared minus 2 times the integral of 1 over v squared dv, or 1/2 times the natural log of the absolute value of x plus 3 squared minus 2 times the integral of v to the negative 2 dv. If we integrate, well, the first one still stays the same, negative, or 1/2 times the natural log of the absolute value of x plus 3 squared plus adding 1 to the exponent, so the exponent becomes a negative 1. Negative times negative makes that a plus. Adding 1 to the exponent. Negative 2 plus 1 gives me a negative 1, dividing by the new exponent. So negative divided by negative makes that a plus 2 times v to the negative 1 plus a constant. Lastly, replacing our v with x plus 3. So I have 1/2 times the natural log of the absolute value of x plus 3 squared plus 2 times x plus 3 to the negative 1 plus c. Now if I rewrite this, Since x plus 3 squared is always positive, I can get rid of those absolute values. And I can rewrite this as 1/2 times the natural log of x plus 3 squared plus 2 times x plus 3 to the negative 1 plus a constant. Or I could do the following. I could bring the exponent of 2 down in front as a coefficient. So that gives me 1/2 times 2 times the natural log of the absolute value of x plus 3, and then plus my 2 times x plus 3 to the negative 1 plus a constant. And then the 1/2 and the 2 will reduce, and that gives me natural log of the absolute value of x plus 3 plus 2 times x plus 3 to the negative 1 plus a constant. So my answer can be written a couple of different ways. One of them is the natural log of the absolute value of x plus 3 plus 2 times x plus 3 to the negative 1 plus a constant, or 1/2 times the natural log of x plus 3 squared plus 2 times x plus 3 to the negative 1 plus a constant.